but he's going to talk about, kind of something we haven't talked about yet, which is actually tools that actually help you do some of it. I mean, Static had talked about it a little bit,
Yeah, so this is more just general kind of ABM methodology stuff than it is social sciences specific. So like Bill said, I wasn't originally planning on presenting, but just based on the conversations, I thought people might enjoy / find useful some work I published a couple of years ago. So I figured I'd show it to you. The original title of the work was Agent Cognition Through Microsimulations, blah, blah, blah. Bill gave it the title, How to Model Agents Reasoning About Agents, which I kind of like more, so I decided to use it, go with that one. So the general problem that we have in agent-based modeling is that agents need to make decisions. So like this sheep here has 3 patches of grass that it could go to. How should it decide which patch of grass to go to? And we've talked about a lot of ways of doing this. Often this sort of the default way of doing this is that just, we'll start out with something simple. Agents just will pick random actions or something like that. So you do see this in this like classic wolf sheep predation model. But you'll also see it, in, I don't know, contagion models with random interactions or something like that. And it can take on more complex things, different frequencies of actions and that kind of thing. And it's often a good start, but yeah. And then we'll often use things like greedy decision making. They're trying to optimize some simple function, like, for instance, in this case, going towards the closest piece of grass. But in those kinds of things, you can only sort of you define what you're kind of optimizing for, and these are agent-based models. Very unexpected and surprising things can happen. So these can be kind of simple optimization stuff can be kind of brittle to that. So the solution that I'm presenting here today, instead of those, is that the agent actually sort of has a little micro agent-based model running inside it, simulating its local environment that it then uses to decide what to do. So using ABM to get agents to decide what to do in an ABM. So agents, in this case, agents have a goal. They have a complex environment with lots of other agents. They have limited information and sort of limited reasoning capacity. And it's not, usually it's not clear about how to get them to actually achieve their goal. So there, we give the agents the tools that we use for this, agent-based models. So a few things to think about here. I mean, I know this crowd definitely knows this, but we want, bounded rationality. Agents should make mistakes, and they should make mistakes in ways that make sense. So, if somebody is navigating a maze and can't see very far, and they're trying to get to that X, the first thing they're going to do is, maybe walk down this corridor or realize they made a mistake, turn back, turn the corner that's closest to them. We realize that there's a wall that they didn't know about here, and then eventually they'll figure out how to get there. And the kind of reasoning that agents do is completely dependent on agent type and what the sort of cognitive capabilities of those agents are. So like a human would behave one way in a maze, and an ant would behave entirely differently. So we want something that allows us to adapt to different types of agents. Right. So the proposed solution is called agent-centric Monte Carlo cognition. The modeler defines, in this case, what actions agents can take, what agents know, believe, which is sort of like how the agent thinks the world, so that's often like what agents can see, what they're aware of. Then what agents are actually trying to do, what their goal is, and then how the agent thinks that the world works. And the way we define how the agent thinks the world works is with another agent-based model. So during each tick of the simulation, each agent runs a number of short simulations with initial conditions based on their surroundings. They will select random actions in these, or we can use a variety of techniques. Simplest way is they just select random actions, see how much reward they get as a result of those random actions, and then they use the sort of sampled reward to figure out what strategy they want to take. And then, so I implement this using the level space extension for NetLogo. The level space extension lets you put NetLogo models open up and interact with other NetLogo models, and recursively, so you can have NetLogo models inside of NetLogo models inside of NetLogo models. So it makes this kind of thing pretty convenient. The other thing is this method is also very, combines very well with other techniques. You know, I use sort of very simple decision-making in these sort of microsimulations, but you can use whatever kind of decision-making thing, as long as there's sort of a stochastic, you can incorporate a stochastic component so that you're sampling. You know, they can do any kind of sophisticated reasoning, whether it's, you know, using factor trees or you know, BDI, agent zero stuff, any kind of thing like that. So I'm going to present an example model. It's totally, you know, a toy model. I picked it because everybody knows it. The classic wool sheep predation from NetLogo. You know, this is often people's like first model. For those that are unfamiliar with it or haven't seen it in like years, the way this works, we have wolves and sheep. The animals will move around randomly. They'll turn left or right, and then always turn left or right or not turn, take a step forward, and they'll expend energy each tick while doing this. The wolves eat the sheep and gain energy from the sheep. The sheep eat grass and gain energy from the grass. And then there's reproduction with a small probability. And they split that energy. When they reproduce, they split their energy with their offspring. And then luckily for the sheep, the grass regrows. So that ends up looking something like this, and it will give you those, you know, classic Lotka-Volterra type oscillations. Cool. So the extension is then to have every single one of these animals running short little mini simulations each tick of the simulation. So we add a few parameters for this: the distance that the animals can see, the number of simulations that they perform, and then the length of those simulations. The actions stay the same, and the reward that they're given, that they're trying to kind of optimize for, is how much their energy changes in the microsimulation. So that is affected by grass, but just also by running randomly. And then when they die, there's a large negative reward, you know, so that they don't want to die. So actually, you end up not really needing that all that much in this case, because when they're dying, they're not eating, so they kind of end up with they don't, yeah, anyway. But it's still.
Or just the neighborhood?
Huh?
Do you run a full-size model or just?
No, so it's just the vision radius. And so you can kind of see it here. I think this is like a vision radius of 5. So that's kind of what makes this possible, right? Yeah, so it's just as far out as they need to see in order to perform the simulation. And while I also note, while in this case, you know, the microsimulation is you know, it's a subset of the macro simulation. It uses very similar mechanics. That doesn't also necessarily need to be the case. If the agent uses a kind of reasoning that is completely different than the real world, or is just a very coarse approximation of the real world, you can use that instead. So in the micro model, it receives an initial configuration based on what the agent can see, as I was just saying. So, you know, and maybe a radius of 5 patches around it. That agent is designated the ego in the model. And then during setup, its first move is chosen for it. Then the rules are basically like wolf sheep predation, except none of the other agents have energy, for instance, because it's not reasonable that that agent would know about the other agent's internal state necessarily. There's no grass regrowth. Again, you know, grass regrowth is hypothetically taking place on a larger time scale than the agent is really probably thinking about in the short term. And there's no reproduction, this similar simplifying assumption. And then all actions are chosen at random. Again, that's just to demonstrate the technique. We can talk more about some more sophisticated methods of doing that later. Right, and so then this simulation is run a bunch of times. We track the energy gained, and then we use a sort of a classic, you know, reinforcement learning kind of thing. Energy acquired later on is discounted, so that they're gonna prefer short-term gain to long-term gain. Yeah, so an example of what a bunch of these rollouts might look like. So this agent is presented with the situation you can see up there, and it starts randomly sampling different actions. So if it goes straight, which I think is that way for the agent, you know, it goes up, and it doesn't actually end up reaching this grass in time. So it does, you know, it gets -3 reward. It tries going straight again. This time, I think it turns slightly right in this step, and it does end up reaching this grass. Yeah, going left doesn't work out. one interesting thing here is that even though this patch of grass is closer to it, these agents coming down from the top end up reaching that grass before it. And so even though that grass is closer, it doesn't actually end up getting to eat the grass. So if we had put in a simple, like, sort of just greedy algorithm here of go towards the closest grass, well, the agent actually realizes here, well, other sheep are going to eat that grass first, so there's no point in me going towards that piece of grass. And then here it goes right, there's no grass there, so it decides not to do that. Cool. Yeah, and then so you probably figured this out, but each tick of the simulation, the model sends the information to the micro model. Agents run the micro model a bunch and then take the action that performs the best. Yeah, so the question is, how much of an effect does this have? Results don't, this is a toy model, results don't matter that much, but it's interesting to look at, like, how much of this do we actually have to do in order to have a big impact on the model, a big impact on the agent's performance? To measure the agent's performance, I'm going to be using their efficiency, which is sort of like how much grass did they eat based on how much grass would we expect them to eat given the density of grass and the number of sheep. And then the sort of the corollary for the wolves with sheep. And it turns out they don't need to do a whole lot of simulations for very long for this to have a big impact. Even at just doing 2 sort of micro simulations at 1 tick, there's like a 25% increase in their performance. And if they do, go out 4 ticks for just 4 simulations, they double their efficiency. So huge gain quite quickly. And we see similar pattern on the wolves. Full disclaimer, you might notice that this wolf graph looks kind of different than this sheep graph. When I originally did this work, the wolves performed very poorly, and then I found that there was a scheduling mismatch between the microsimulation and the macro model. So this is the cleaned up model that's actually going in my dissertation. So right, which I was frantically collecting last night since I decided to give this talk yesterday. Yeah. And then we see similar, like, just gigantic effects on the population. So here we're looking at the y-axis. We're just looking at the average number of sheep compared, again, with the number of simulations that the agents are performing and the length of those simulations. And you can see even with the short number of simulations, the number of sheep just at stable just gets gigantic. When the wolves, similar thing happens. We're again looking at the number of sheep here. The wolf dynamics are kind of weird because, the more efficient a wolf is, the less food supply it has and the less quickly it reproduces. And so you get kind of a, pretty weird shape there. So just looking at the number of sheep coding gives you a cleaner picture. So similarly dramatic impact. You'll notice, so the shading here is the 95% confidence interval. This here is when they start to get so good that they eat the sheep to extinction. Yeah, so that's what's happening there.
Just to confirm on the results, are the sheep and the wolves both using that?
Oh, I'm sorry. Yeah. I should have said that. So these are two different parameter sweeps. I'm sorry. I should have said that. In these runs, we're just leaving the wolves at random and letting the sheep go. In these runs, we're just leaving the sheep at random and letting the wolves do their thing. You can combine them as well, and figuring out how to compare them is really interesting. But just to keep things simple.
One of the pathologies of this model is that it's actually very unstable, this model. And if you let it run for a long time, often that just collapses. Yeah.
What's that? Oh, yeah, so that's actually interesting. Yeah, the BaseNet logo wolf sheep predation model is extremely unstable, which was very frustrating when I was initially doing this work. When I when I was cleaning it up to put in my dissertation, I created a more robust version of the model, which just sort of tweaks some of the base rules in ways that kind of make more sense anyway. And that ends up allowing for a lot more stability.
I'm curious.
Huh?
What
What were they? Yeah, so there's rather than in the base model, reproduction is just based off a percentage.
Yeah.
And instead of that, I switched it to a threshold way, so they only reproduce when they're healthy enough to reproduce, which kind of makes sense. And that makes the model just extraordinarily more robust. The wolf threshold is basically a parameter for how robust, how stable you want the system to be. I also made it so that the wolf energy is based off the sheep energy. I mean, the amount of energy that the wolves get is based off the amount of energy that the sheep had, which again, makes sense. So yeah, so reasonable modifications that let me explore the parameter space a lot more. In the base model, actually, I think that these results just collapse pretty quickly. Yeah.
Are you going to tell us about results about whether you have both populations optimizing?
I can show it to you, but I don't have the results in this slide deck.
Just qualitatively, is the thing more stable or less stable? My intuition is
Oh,
less stable.
yeah, it does get less stable, especially, so the sheep tend to, once you have smart sheep, wolves need to be a lot smarter to compensate for that. It's easier to, not get eaten than it is to eat something. Right. So it does make it less stable, but you can find, there is a stability curve. I don't have those results here, but once I finish recollecting the data for this, then I'll have those results. Any other questions about that? I was trying to go fast, so I think I skipped a few things.
I mean, I think the related question to that would be is that, like, so here you're showing wolf efficiency and sheep efficiency as your optimization to some extent. I mean, you're not
Sure.
optimizing it.
I'm not targeting it. They don't know anything about that, right?
But it would be very interesting to look at, like, some sort of, like, community health measure. I don't know what that would be in this case, but,
Sure.
is there an optimal level of cognition that wolf and sheep need to maximize the robustness
of the system as a whole? Yeah, for sure. I mean, the efficiency measure does a little bit of that by controlling for population stuff. Like you can be, like the sheep are a good example. They can be, you won't reach a point in their efficiency, like realistic efficiency, where they wipe out the grass. And even the wolves can get pretty efficient before they hit instability. But yeah, that would be really, really interesting to look at. Yeah.
Like
Oh, I'm sorry. Yes.
Can you show us, say, does this affect the time series at all? I mean, it's always flopping around.
Yeah. So I don't have. I can show you the time series if you want. But I don't have it in the plot.
If it tamps down the volatility, or
it increases volatility in general. Yeah. I mean, yeah. This is to Rob's point. It definitely increases. More efficiency definitely increases instability, like for sure. Yeah.
There is a recent paper, maybe somebody, I don't remember the author, Neil Johnson, there is a paper about, kind of multi-agent environments, swarm environments. You want the agents, if agents are too dumb or too smart,
yeah,
it's very unstable. So it's some interior kind of Goldilocks
point. Yeah. Absolutely.
I wouldn't agree with Rob on that. In that I agree, and I'd say that what it does to volatility to me is unknown. I'm not sure, especially if you had
sure.
guys going back and forth.
We actually
some in between.
Sorry, give me that. No, we published a result on that at that old agents conference.
Yeah, right.
On the L for all bar problem, where we actually went from agents who are extremely dumb to agents who are extremely smart,
yep,
using the number of generations of the genetic algorithm to control for how smart they were that we were running, and we found exactly the same thing, that like there was this optimal Goldilocks solution that wound up optimizing not just the individual agents, but also optimizing for the community as a whole,
yep,
right? Like in Bryan Arthur's original problem, if the agents are too smart, you don't get that 60 optimal value.
Yep.
And if they're dumb, you don't get that 60 value. We plotted his results on there too as well. I think he got a little lucky. Like he just happened to set up the rules in such a way that they happen to be in place, right?
Funny. Yeah, I mean, so one nice thing about this technique is that it's so easy to do that kind of tuning, to search that space of like how smart things are. And so I'll definitely have to do that cross and figure out what that optimal level is. So deciding like what the healthiest ecosystem is, I'm not.
Quick question.
Yep.
The
So there is no learning in this case. So yes, but that's because there's no, they're homogeneous. I've done it with heterogeneity as well. Yeah, but it, yeah. Oh, just to give a sense of some of these numbers, if you just set the sheep to always go towards the closest piece of grass, they get an efficiency of about 2. If you have them also try to avoid wolves, their efficiency drops to like 1.5 or so, or maybe it might be 1.8, I forget, I can look up the value. What's interesting here is that the sheep are naturally going towards the grass that they can actually get while avoiding sheep, but there is no, there doesn't seem to be much of a trade-off between those two. So I think, this is obviously, it's a toy model, it's very basic. One thing that excites me about it is how many directions you can take it in, though. So there's a number of problems with this technique. So it's very naive, at least as done here, it's very naive. It explores a bunch of futures that just don't matter, that, it's assuming the other agents are going to be doing random things, which they're not. It's exploring actions that are just very quickly determinable to be bad. So this can be solved by fixing that trying actions at random thing. Also, incorporating learning would be a really nice progression of this. I've done a little bit of that, but some of the easiest ways to solve this is adopting something called Monte Carlo tree search. Some people here are probably familiar with it. I'll talk about it more in a second. Into those rollouts. With learning, we can do reinforcement learning. We can do evolution. It's combinable with all these kinds of things. And then doing predictive modeling of what the other agents are going to do would be very cool. And then, of course, because we're doing sort of recursive agent-based models, we can go deeper. Put ACMCT inside of these micro models again for as long as it goes. That makes my laptop very unhappy when I do that, as you might imagine. But there's some clever tricks that we can actually pull here. And then combining it with other, domain-specific techniques would be really cool to see, agent zero, factor trees, like I mentioned, to actually apply to real domains. Like, the nice thing about it is that it does sort of just naturally enhance any other technique for some, definition of enhance. So the MCTS thing, a really easy way that we can solve some of the naivety of this is that you take the reward values from past samples, feed it back into your action selection, and then use that to influence which futures you're sampling. So you quickly narrow in on the futures that are actually interesting to look at. So like I was saying, getting agents to think about agents thinking is like the kind of fun thing to think about, but gets pretty impractical pretty quickly. Luckily, we can actually combine this with, we can kind of pull a trick with MCTS to do this in a flat way. So instead of just keeping track of the ego's reward, we can keep track of all of the agents' rewards, and then feed those reward values back into the actions that they take in the initial model, and then so they're all sort of like sharing that microsimulation together and getting better from it together. Now, this is just the ego's reasoning. So it's basically, it's sort of thinking about, it's really good if I go left, but, it also seems good for this other agent if they go right based on what I know. And the reason that this is okay to do is because it's all based on what that ego knows. So they are sort of simulating what's good for the other agents while figuring out what's good for themselves. So this lets you do that kind of recursive thing without actually going recursive, if that makes sense. Some related work. Markov decision processes are a super related thing. Monte Carlo tree search, multi-level agent-based modeling. This is an example of I don't see a ton of like agent decision or cognitive applications of multi-level of ML AMBM. So that's one reason I was excited to do this. And then NetLogo, of course. I'm in the NetLogo lab. So, yep. Thanks.
Thanks a lot for the level space, Bryan.
Oh, sure.
I actually have a question that might be tangential to
Yeah.
the wolf sheep predation work, but something I've been thinking about, and it's great that you're here that I can ask. Could we use level space to potentially parallelize NetLogo? Could we have each of the agent, because do they run on?
Yeah,
I think they
so-
run. Each model runs on different threads, right?
Right, so that's a great question. Yeah, level space tries to be pretty smart about it. If you ask a bunch of models to do something, it will run those in parallel if you meet like a sufficient number of models to beat the overhead of parallelization.
Okay.
So it does parallelize, and it tries to be smart about that parallelization because there is an overhead to parallelization.
Yeah.
One caveat I always throw in about parallelization conversations, though, is that we're usually doing parameter sweeps of some kind or rule sweeps in the IGSS case. And often you're just going to get better performance from parallelizing across that parameter sweep rather than within a particular model.
Yeah,
but if you have just a gigantic model, you can definitely use this to parallelize stuff.
Right. So we could partition out the actual simulation. Like if you have 1 billion agents, you would have maybe 1,000 running on each.
On each of those.
And then you have a meta model which is controlling each of those.
Yep, that's exactly right.
That's possible. And then each of the partitions would run on their own thread. Is that correct?
They each run on their own thread.
Okay.
Yep.
Okay, great.
Yep.
Yeah, that's exciting.
Yeah, and we can talk more about the technical. There's a lot of technical stuff there.
Okay,
that's good to be aware of.
Yeah.
I tried to strike a balance between ease of use and also performance stuff.
Yeah.
Okay.
So if the sheep get a lot smarter about avoiding the wolves,
Yes.
one tactic that the wolves should take up is to hunt in packs.
Yeah.
Any way to get the wolves to do that here?
Yeah, that's, I haven't done much sort of, qualitative analysis of the emergent behaviors. And partially, so I'm trying to develop some techniques to do that kind of thing. If people know about, for particular examples, when I know what I'm looking for, if I'm looking for packs, I know how to detect, I can think of ways of detecting that. But it's the stuff when I don't know what I'm looking for, when unexpected emergent behaviors pop out, looking for that is obviously
I think maybe a more interesting question would be, could you get packs to evolve?
Sure. Yeah.
Like could you give wolves the basic primitives, and then so that they could evolve them over time? And obviously, I don't mean it's like literally evolving the ACC
That's the intent of the question is
code to do it. But
with these rule systems that define your agents, how do you get access to the emergent properties of the agents that are the interesting thing and to start with?
So I've been doing I've been doing another portion of my dissertation is looking at ways of detecting emergent behavior in agent-based models. And I've had some limited success in simple cases, but I haven't applied it to this yet. So we can also just look at it and kind of see, are they kind of hunting in packs? We probably don't have time to look at it right now, but if you're curious, we can try that out later.
A nice comment is that the Lotka-Volterra model has an assumption of perfect mixing. So it means that the correct representation is that each wolf jumps to a random patch each time. There's no movement. Now, the NetLogo version has some movement, random walk, which is a little bit different. This is complete something else. So it might be that the random mixing actually makes the system much more, it oscillates much less the random walk or this approach. So maybe, I'm not sure, but maybe the perfect mixing actually reduces the volatility of the model. And here we get this is actually much less random than before, and then we get all this, you might have a larger oscillations, I'm not sure.
I'm a little curious. That seems like a little bit of a perverse way to approach the problem, right? So you're saying we should deviate from the way wolves actually move in the real world, so we can better match the analytical results?
No, I'm saying something else. I'm saying that we should be part of the explanation why we get all this, because why does the NetLogo version is so volatile? Because the equations...
Populations are volatile.
Yes. Two things happen. You have a finite population, so extinction is possible. In the Lotka-Volterra, it's an infinite number of people because you have half a wolf. And also maybe the multiplication, like the beta time, wolf time, sheep, has a different interpretation than these things. That's the way to think of it.
Yeah, I find like we should make the models more realistic, not more like the.
No. This is better.
Right.
It's much better.
Yeah.
Much better.
To respond to Bill, actually in the real world, wolves don't move like this, right? They move in packs and hunt in packs.
But they move, this is
They
a
do-
closer
it's closer.
approximation to them randomly disappearing in one section and reappearing in another.
Maybe it means that the random movement is closer to the packs. The full mixing.
Okay, so just anecdotally,
We haven't shown any real data at all in this.
Yeah.
right. So just anecdotally looking at the model, you do get wolves that kind of look like they're surrounding sheep and stuff like that. I'm not going to say that those are packs. That's anecdotal, qualitative. I can't stake anything, but just for what it's worth. On that point, since doing that work, I've done a bunch of sort of baselining against like, kind of obvious strategies like, suppose they're randomly teleporting, how do they react to different smart strategies and stuff like that. Random teleportation kind of squashes, all interesting behavior. Right, of course, yeah. But yeah, just a small little
But this is not the Volterra, it's different than this, it's something else. Similar, but not exactly the same thing.
Right, yeah. There's also, I don't know if you know have seen the rock, paper, scissors 3 species ecosystems. There's sort of these 3 species cell-based ecosystems that create these sort of beautiful spiral shapes. And the interesting thing there is that when you just look at the differential equations, they're extremely unstable. They fall apart almost immediately. And when you discretize them and look at the spatial, it takes longer than the universe for them to actually collapse. Anyway.
I just have a couple points. Well, one is on your literature review, there was not very much old stuff there. So I'm just going to badly date myself here and say that somewhere around 1991, okay, sitting in Santa Fe when Langton was making Swarm, and I asked him, well, why do you use Objective-C? Of course, now one answer for Objective-C was next, okay, but another one, but his positive answer was, well, it's so late binding that I can basically have agent-based models
inside
which so that was the main motivation for Chris.
I cite that in the dissertation.
Oh, okay.
I don't cite that up here. Yeah, I go through the history of multi-level agent-based models and the ideas behind that.
And at the time, I remember asking him, and he said he thought that this idea would in fact be a dominant one in some areas. I mean, Chris thought in ecology, of course, you want to have individuals with modeling the individuals that they're preying on or being preyed up. So anyways, that's the anxious.
I hope so. Yeah, the point of this is not that so much that it's actually a novel idea. I think almost everybody going through this stuff thinks, oh, wouldn't it be cool if we could put AVMs inside AVMs?
It's almost never been done.
But yeah, this is like
rarely been done.
This is possible and actually pretty easy to do, and even it's way more practical. The point is way more practical than maybe we would
talked about it.
It's always, I think it's even in the construction of.
Exactly.
It is. Yes.
Mini Swarm.
Exactly. Right. Yeah.
But
nobody uses it.
No one did it.
The logo for Swarm has it as an agent system with little agent systems inside agent systems with little agent systems. Like the logo has it, but no one's done it.
But I'm pretty sure if you go back to ecological modeling in 93, 4, 5, 6, there are a couple papers which do it.
Are they hypothesizing about it, or are they actually doing those?
I mean, there are a couple swarm models.
Swarm models of it, yeah.
But
again, when I do the history of this stuff, I talk about Swarm a lot.
But then the other thing I wanted to mention was that, I got it a little bit wrong. So it is Neil Johnson. It's Science Advances from 1 year ago, where he has this business about if you have a performance goal for the whole community, then you want to have your agents be better than random, but not too complex, too sophisticated. Otherwise, it's very hard to engineer the system. So
it's called to the goal by being less capable.
Exactly, you got it, Bill. And the Science Advances,
February 6th, 2000.
Bill, can you just email that title to me so I don't have to be on my phone when I'm up here?
I think that all of the agents are pretty much have the same capability. That's a whole other angle.
Well, in repass as well, the original goal for repass was very similar. The name of the repass, actually, if you take it out, is Recursive Forest Agent Simulation Toolkit. The idea, again, was that you, all of us had this, and no one's done it.
One last thing, just I've tried. So the other kind of obvious thing to do is like stick up. So in techniques like this and AI stuff in MCTS, you often stick big neural nets that are trained on the output of the MCTS and then also used to guide the MCTS to that tree descent. So I've also tried to do that here, both like predictive modeling of the other agents and to guide their own behavior, and it goes very slowly. Turns out running thousands of neural networks, thousands of times a tick. Yeah. But anyway, just a...
Yeah, quick observation. We talked about wolves forming packs, but also a lot of herbivores like this, they form defensive herds themselves.
Yeah, good point. Yeah.
So it wouldn't just be the wolves doing this. It's when it's the fully modeled sheep should actually form defensive perimeters.
Right. So there we get some I mean, I think this gets to some of the important things that IGSS can do for us. There's nothing that would allow that to happen in wolf sheep in wolf sheep predation as defined. The rules, just the physics aren't in there for it. And so being able to have a tool set that we can apply that would allow for that to happen. I mean, one nice thing about this technique is that unexpected behaviors can absolutely arise. You can totally see you could see, I mean, I'm not saying I've seen it, but wolf pack behavior coming out of this or something like that. They do fairly sophisticated reasoning, but you're still bound by the limits of the rules of the model. Yeah.
Oh, actually, sorry, I understand there's no algorithm or anything like that in here, but there is a behavior that would allow that to emerge, which is, I always want another sheep between me and the wolf. and
Fair, yeah.
If you ever played that game, somebody...
How are the heroes?
Heroes and cowards, yeah.
Sword Shield.
Heroes and cowards?
Yeah, it's the same one.
It's the same one, okay, yeah.
Yeah, Heroes, Cowards, Derivator, Sword Shield.
Yeah, I would love to do just more, qualitative analysis of what behaviors pop out of this for that kind of thing.
But I want to go back to Steve's point about having herds form.
Yeah.
So now when it comes to people doing biology of schools, swarms, et cetera, there has grown up in effect. There's fairly sophisticated, both empirical literature on how do
of course.
The schools behave. But it's usual to distinguish there between three different modalities of the individual behavior. So you would say, how does the school evade the predator? How does the school of fish avoid the shark?
Uh-huh.
And then so a new fish to the school has to learn behavior of the schools. So they consider that group learning.
Interesting.
For example, there would also be how would an individual learn to avoid the shark?
Yep.
And the claim is this is now this guy who used to be at Princeton, now he's in Germany. Ian Kusin,
Yeah.
And so Kusin's work really shows that the fact that you learn well how to avoid the shark in the group setting does not give you any good ability to avoid the shark by yourself.
Yeah, absolutely.
Completely different things. And then there's this intermediate case. So the individual learning is you against the shark. Group learning is school against the shark. But then there's also something called social learning. And social learning is an intermediate case where you are now learning from other people how to learn from other people like you how to avoid. So then now the question is to evolve all those different mechanisms. So you now have a sophisticated IGSS program.
Yep.
And Rob, if we just stuck a void behavior there, that they would start to form swarms like that. That'd be very straightforward. And each of the parties would form a void cluster, and I think you're going to see some swarm behavior. I'm sorry to jump in, but to me, going back to the explainability thing, it sounds like there's several different ways that this behavior that we observe could have emerged. Yeah, right. And what can IGSS tell us about what's the mix of those things actually operates in the real world?
Or how much data would you have to have in order to produce robust behaviors?
Yeah.
It's like you have to find other consequences of each of these things to try to distinguish them based on that instead of the herd formation.
Yeah.
Cool. Sweet. Any other questions, points, conversations? Oh, yeah.
Just wanted to make a quick comment. As I mentioned yesterday, whenever I think I have an interesting idea, so start searching for it, realize that somebody have done that. So I'm just glad that you have done that.
Yeah, when you said that, I was like, uh-oh. Yeah.
I just have like one technical question is if you looked at what is the exponential time, performance time, exponential growth of performance time, depending on how far out in time each agent has to look.
Oh, you mean just fitting that curve?
Right. So when you look at the
let me get back to this a second.
Of course, the baseline, and then 1 steps, 2, 3, 4, and so on. So what will be the incremental growth of runtime? So is it exponential, or is it less than that, or more than that? So
right. So we can derive that from these graphs. Is that kind of what you mean? Like, what is this? So if we get that sort of optima, if you break this out into a heat map and trace that optima out, and then
So that will be very useful, because this is what we would really like to implement. For example, we have, when you call your agents wolves and sheep and just make a picture of wolf and sheep, you start thinking about ecology.
Right.
But of course, we do use the same kind of models, but for drug users and drug dealers and police, and we also using the same formulation for job searches and stuff like that. So there are many applications, but just could be very generic. So yeah, if you have it publicly available, would be really great to
so all of this is on GitHub. Netlook is open source, of course. Level Space is open source. This model is open source up on my GitHub. I think I have to I have to push again to get the most up to date up there. But happy to link that to you. And then this was published a couple years ago in IGSS. So
it's really a beautiful point. I mentioned once you go from 0 to 5 here.
Yeah.
So it is the case that in behavioral game theory or experimental game theory, there is a class of games where you observe players playing the game, and you can then deduce
how far ahead they're looking.
How far they look ahead.
Yep.
So these are the K-level rationality of Rubenstein and Cameron, et cetera.
Yeah.
And the usual result is, you look at it, it's quite modest. It's typically going to be 1 or 2. But a lot of people are doing 0.
Yep.
And so I think that, if I remember right, maybe Blake or Chris knows more, but I think that the mean was something like 1.5.
Yep.
Right. But also it was heterogeneous in the population. It was very heterogeneous. And there are occasional people who do 5, 6. Right?
Yeah, so I think one of the most cool things about this is then, because people are using all sorts of heuristics when they're playing games, for instance, and of course, animals will be using all sorts of heuristics in the wild. Combining those heuristics with this to sort of mutually benefit each other, so that maybe we just we go out 2 ticks or whatever, but because they are using some heuristics, it's more guided than that. And we can look at the systematic mistakes they make and stuff like that, and compare this.
For that particular game called K-level rationality. I did have a student a couple years ago. Some people really know. When I say his name, you'll recognize the formidable level of analysis he brought to. Maciek built a model of K-level rationality where K can be anything. In fact, he also had a body of M. The software supports K anything, and it also supports. If I remember right, for a population of N players, you can have any number of Ks for the population, and it automatically creates the software to solve that accordingly. So, I mean, this is much like at a finest.
Interesting.
He wrote it in Mason, so that piece of code exists somehow.
That'd be cool. That'd be cool to look at. Yeah. Cool. Anything else? Everybody hungry? All right. Thanks, everybody. Oh, and thanks again to Bill for letting me jump in. Yeah.